The origins of this approach, actually, I think the first paper we reference is an Australian paper by Westoby, where I think it was the first attempt that we know of in the literature of trying to characterize the dynamics that occur in vegetation communities using states and transitions. And so in this example from the Westoby paper, the states represent different vegetation communities, and the transitions represent the processes, either natural or management, that can move you between those states. So this is an approach that I know you guys still used. Anna shared with us some of your documents that follow on from this, but these are the conceptual form of state and transition models. And what we're going to be talking about today is what we call state and transition simulation models. So we've coined this term. We've added the word simulation to the state and transition model. And this kind of approach dates back to the early 1990s. It's before my time, before Leonardo's time, but during the time of some of our colleagues in the early work of this stuff. And it was really driven by some scientists in the Western US who were faced with trying to model mixed vegetation communities. This is in the Western US, where you have sort of mixed shrublands, grasslands, woodlands, all interspersed on a landscape. And to this point, there had been a fair bit of work modeling. There are still today numerous models that work exclusively in forested systems that had been sort of well developed by this time. But this group was faced with this challenge of trying to develop models that worked across different vegetation types seamlessly across a landscape. And they kind of started to develop these techniques then. And since that time, as you'll see in the examples we show the next 2 days, they've been applied in a really wide range of different systems. I think that's one of their huge strengths, is that they will work in essentially any vegetation community, any two-dimensional vegetation community. We have applied them. You'll see, I'll show you an example in a bit, in 3 dimensions, in sort of wetlands, and we can talk a little bit about how that could work. But really, at this point, they've been applied in 2D. But we even have an example. There's a paper of some work that's been done, using the approach for modeling coral reefs. And so the software is agnostic to the type of vegetation you're dealing with, and to the interspersion of that vegetation across your landscape, importantly. So here's a little bit of the history since the start of the tools in the 1990s. So there's a company that both Leonardo and I used to work for before we went out on our own to start the company Apex that we're working for now. We've been together for, well, I left ESSA 13 years ago, I think now. Leonardo, not quite so long ago. But when we were at ESSA, it was a company, again, another Canadian company that in conjunction, mostly at the time with the US Forest Service, they were the kind of lead developers of this. They developed a software tool called VDDT. If you Google it, you can still find stuff on it. And it was a non-spatial version of this kind of modeling tool. And Louis worked with VDDT. Leo has worked with it as well. We all have, because we kind of date. I think Leonardo, you date from around the year 2000. Is that right? Probably.
Yeah, 2002.
2002. So Leonardo and I kind of came into the middle of this when we were working at ESSA. And there was a second product called Telsa that was trying to deal with the spatially explicit side of things. And eventually we realized these products had kind of met their life end as a software product based on the technologies that we're using. And we set out, Leonardo and I, when we came in, to develop a sort of new software platform. It had a name at first called Path that we changed to STSim. And this really got released in 2013. Again, I started working on my own around the time of the start of this, 2007. So this is a sort of second generation of these software products. These don't get used anymore. STSim is the only thing that I know of that really does this kind of stuff at the moment. And I think a key point in the evolution of these products is 2016. I actually went back to school to do my PhD. I think it's 2012 or so. So I had some time finally to deal with all the theory behind the tools we were developing. So I took a big step back and I published a couple of papers. And this is sort of the foundational paper now for our software that describes the sort of math and techniques behind it. And so again, actually, I should probably circulate that paper, but you can find it online if you like. So how does this state and transition simulation model approach line up against all the dimensions of models that I sort of ran you through quickly on the previous slides? It's definitely a quantitative approach. It definitely leans to the empirical side. It's very data-based. You can, as I said, there's even you can see in this diagram here, there's some process assumed in how we model transitions between states, what states we pick. So it's not absent a process, but it is on the spectrum of models out there for modeling landscape change, quite far over to the empirical side. It's fundamentally stochastic, as you'll see. It works with probabilities and distributions at its core, which makes it very capable for dealing with uncertainty. Although I think as we'll go through the 2 days, you'll see in theory it has all the levers there for sort of fully characterizing uncertainty and projections. In practice, our experience has been that it's a very, very big lift to do a really good job of uncertainty analysis and modeling, and it takes a lot of work, a lot of data, a lot of understanding to do it well. It's a simulation model, obviously. It's we're going to talk a little bit about the approach in a bit, and it can be run, as we'll show in the first exercise, in a spatially referenced form, but most people, it has the full capability of doing spatially explicit simulations, and most of the work we'll do over the next 2 days will be spatially explicit. So any questions before I sort of launch into a series of slides that give you an overview of the mechanics of the modeling approach? No, we're good.
I just sent a PDF of the paper to everybody that was on the course mailing list.
Okay. So here's a series of slides that runs through what you'll find in more detail in the paper we just referred to. But this is how a state transition simulation model, or STSM, as we shorten it, works. So you take your landscape, it could be any landscape, any vegetation community, and you divide it into a number of discrete cells. So that's kind of step one. And you have to decide on a nomenclature or a currency for which you want to represent what we call states that each of these cells can be in at any one point in time. So in this example, I've decided to classify my landscape into 3 possible states, but these can be anything you want. And you also have the option in these models to also assign an age to each cell in your landscape. Now that's optional, but it's available for you. So you start with your landscape. Each cell has a state and age, and then we develop we call a pathway diagram. So this is a diagram you develop that describes the possible transitions that can take you from one state to the other. So you've got, again, you set up your currency for modeling as the states and the transitions you wish to recognize, and you come up with a pathway diagram like this that describes how these states can change in any one cell over time, and typically you assign probabilities to those transitions. But we'll talk in a little bit more detail about the other options for how to specify the level of those transitions. But once you've done that, you can then sort of simulate forward the state and age of each cell over time. And these state and age, they're random variables because every time you run them, you're moving them. The state is changing from one state to another, and the age is changing in response to your probabilities that you run through that pathway diagram. So once you're done, say 40 years later, if you've taken this pathway diagram, you've got your initial state and age, you've got a future state and age that you can project for that cell. And we can repeat that across all our cells, and we can get a projection for the state and age of every cell in our landscape. Now, because we're dealing with probabilities, every time we run one of these cells through that pathway diagram and we play it as a game, we can get a different projection for the state and age of every cell, so there's some variability. And so this is how we get some variability or uncertainty in our projections. We can run this over multiple, what we call Monte Carlo realizations, and end up then with a distribution for the projections for state and age over time. And so some of the key features of the approach is, as I mentioned, in its simplest form, you can represent the transitions that occur like I've done here for fire using probabilities, and these are probabilities per time step. If it's typically an annual time step, these would be annual probabilities of transitioning. But you can also use age as a second state variable, so you can make your probabilities conditional on age, or your dynamics conditional on age, so you can add some richness that way. And importantly, you can choose to represent any of your transitions, and this is typically used for management-oriented transitions. You can express the transitions as targets instead of probabilities, so you can fix the amount of area that you want to transition, or fix that certain cells will transition, force them to transition under certain conditions. So not all transitions have to be represented as probabilities. And just to highlight how this, some people say, well, this is very close to a Markov chain, if people are familiar with Markov chains. And so the key differences to a Markov chain is, one is these targets, but the second is that you can have multiple pathways, as I show here, leaving C back to D, for different processes represented in your model, which is something you can't do in a classic Markov chain. And now a couple words on software then. So that's really all that there is to the approach. On the software, yeah, I see there's a question, is there? Yeah. Is age able to be substituted for time since last disturbance? That's a very good question. So I kind of brushed over the time since last disturbance. When we use age here, we'll get into it a little bit into the exercises, but age in the end, if you read the paper, turns out to just be a counter that you give the label AGE to age. And so it's up to you to define what age means in your model. And in fact, when you get under the hood, you'll find that you can actually, you don't just have a single age or counter that you can use as a state variable. You can have a counter for the time since every transition that you're representing in your landscape. So in this example here, what do we mean by age? We could define it as the time since fire, or we could define it as the time since fire and or harvest. That seems to be what's kind of implicit in here, is that any disturbance, whether it would reset your age to 0, or we could define it any way you want. So there's a great deal of flexibility in how you represent these counters. And to simplify things, I just refer to it as quote unquote age at this point. Does that make sense? And so back to software. So we'll be talking about two different terms here, SynchroSim and STSim. So just to clarify the difference, SynchroSim is the software you all installed, and it's actually a general modeling framework that supports models to be plugged in as packages. And we use it to model population dynamics. We use it to do connectivity. We're just starting, we've just got a big project with the federal government here in Canada to use it to model COVID-19 epidemics. And so it's a framework for any kind of basically stochastic space-time model. And STSim is just one package that we're going to be using in this course. It's our sort of landmark package. It's the one that most, has the longest history of being used by SynchroSim. And so it's one that's packaged within SynchroSim for developing state transition simulation models. So that's the difference. And these things, the STSim is open source. I think almost all of our packages, if not all of them, I think now are open source. So we make the science and the models open source. The software itself we keep it as it's proprietary. It's our company owns it. And so we liken this kind of to, the model that I say our studio does, where our studio is ostensibly at some level open source, but essentially closed source. Yet it's an environment that's designed to support open science and to developing open source models. GitHub would be another example of a similar model that's a closed source environment in which open science is done. So it's very much like the way we try and run SynchroSim. And we give it away for free. And the reason we're able to give SynchroSim and STSim away for free is that for the past, well, it dates back probably 25 years, but 12 or 13 for STSim in particular. We've had support from a number of most of US government agencies, shown here on the screen are the big contributors that have supported the development of software over the years. And in fact, often because we have a whole community of developers, when one of these agencies falls short of funding, the others tend to step in, and we've been able to get this real continuity in the support and development of the products over more than a decade now. I think that comes from having multiple agencies at the table able to support it. So that's sort of my intro. Any more questions before I go into a little demonstration of the algorithm? So I'm going to try and take you through the algorithm in a little bit more detail. Any questions? Good. Okay. So what I'm going to do here is and this is the first time I've tried it like this. This is an exercise we probably still would do if we do another in-person version of the course. So this used to be our first exercise. So you as participants would play a board game. So you'd play the STSim board game. So we're going to play the STSim board game together today, but the last time we did an online course, we tried to do it with the participants all playing, and it was a little slow and cumbersome online. So today I'm going to try, and I'm going to play the game, and you're going to watch. So hopefully it'll go a little bit smoother. It might not be quite as fun for you, but nonetheless, I think we're hoping it'll work out well. But this is a first to try it using this format, so bear with me a bit. So what we're going to do is we're going to take a landscape, and I am going to simulate it forward in the same way we would with STSim, only I'm going to do it with dice and a playing board. So it's just going to sort of try and drive home the basic algorithm that I described in the previous slides in a little bit more detail with a simple example. So this is my landscape. My hypothetical landscape is only got 16 cells in it. We used to do it where there was one cell per participant in the course. So you could still imagine this, that if each of you were playing this game, you would be doing this in parallel with me, and you would be each modeling forward your cell in the landscape. So I'm going to take one cell and show you through. I'm going to take this top yellow cell, and I'm going to follow you through the simulation process, but you can imagine we would be repeating this. So we have a landscape at time 0, and this is a landscape that we've decided we're going to model with 3 potential states. So this is our pathway diagram up here. And so this is a shrubland community. If I remember correctly, this is Leonardo's example originally. You can correct me if I'm wrong on anything here, Leo. But this state, any cell in this landscape, could be in any one of these 3 states at any one point in time. So it can be in this open community. And so this is, it's an open community. I can't remember exactly how it's described, but it's sparse vegetation, maybe grasses, not a lot of woody vegetation yet. And you can be in that for up to 2 years, age 0 to 1. And if you stay without any disturbances occurring, you will go through succession, move into this closed state. And so you can end up, a cell can end up in this closed state, whereas now you can imagine there's more, say, woody vegetation on the cell, and it can stay there, in fact, forever in the absence of any disturbance. But if a fire comes through and burns this cell, this fire will move it back to this open state and will actually set its age back to 0. So in this model here, the age is representing the time since last disturbance, of which 1 is fire. Now, the other thing that can go on in this landscape is you could be in this open state. And when you're in this open state, you're vulnerable to invasion by some exotic species. This invasion can happen with a certain probability, and you can end up in this exotic state then that you're stuck in forever unless you apply some management, some restoration to that landscape that can move you back into the open. And so as you can see, once you're in this closed state, you're not vulnerable any longer to this invasion. You're only vulnerable when you're in this open state. So that kind of makes sense as the ecology of what we're trying to represent here. And so this is a simple 3-box model, but as I'll show you in a minute, it's not so simple that it might not be used in a real applied project. But what we have simplified is the probabilities I'm going to assign to each of these transitions. So I've made them divisible by 6, the size of a die, so I can run this model with dice. But you can imagine here what we said is that we're going to assume that the annual probability of burning is 0.5 per year. So that means every year there's a 50-50 chance that a closed state will burn, in which case if it does, it gets set back to open age 0. And so when we roll a dice, if we roll a 1, 2, or 3 on a 6-sided dice, for a cell that's in a closed state, we'll move it back to the open. If we roll 4, 5, or 6, it means a fire didn't occur and we'll stay here. And similarly, we've assigned the probability of invasion to be 0.33 and the probability of restoration to be 0.167. So those are the probabilities we're going to put into our model. And so that's the first thing we needed. We have our pathway diagram with our probabilities. The second piece that we need to start running STSIM is to be able to initialize our landscape. And so normally you would have a map of your current conditions at time 0. In this case, just for the example, we're just going to start the landscape assuming it's all in the open state. And we're going to say in this case that we unfortunately don't know the age. So we didn't measure the age, which is a common thing that happens. And when we run these models, we often get models, initial conditions derived off of maps of state, but we don't often have the age. So we'll take you through what STSIM will do in this situation. So this is our original map data. Everything's in open. And now what I'm going to do is I'm just going to walk you through how we model this one cell from time step 0 through to time step 5. I'll do that on this next slide. So this is the playing board. So this is my playing piece. This piece is going to represent my trajectory of my random variable, which is the state of my landscape over time. So as I told you, we're going to start the model in time step 0. We're going to put it in this open state. So that's where we start in time step 0 for this cell. And the first thing we're going to do is we don't know whether it's age 0 or 1. So we're going to roll the dice, and I need a die. Let me go get one. Got ready for this. Dice roller. I want one. Can I fit this? Whoops. roll the dice. This dice is taking up a bit too much room on my screen, but maybe it'll fit over here. Will it fit over here? Yeah. Okay, so I'm going to roll the dice, this one die once, and I get a 2. So I'm going to put a 2 in here in my board game. That's what I rolled. I rolled a 2. And so the rules for the game are down here. For initializing the age, it says roll the dice once. If your roll is a 1, 2, or 3, your initial age is 0. And if your roll is a 4, 5, or 6, your age is 1. So we rolled a 2. That means my initial age is going to be 0. And so at the start of my simulation, age 0, at the very end of age 0, my state is going to be open, and my age is going to be 0. So you can see, whoops, you can see already that we're using a random number generator to generate an initial age when we don't know it, right? And so in this case, for this realization of my simulation, I'm going to assume the age is 0 because I don't know it. I picked it with a 50-50 chance of being 0 or 1. And now what I'm going to do is I'm going to roll the dice again. I lost my dice. I'm going to roll it again to decide what happens with respect to all these transitions. So let's just roll it. I get myself a 5. And so let's put the 5 in here for time step 1. I got a roll of 5. So I'm in this open state, and it says if I roll a 1 or a 2 when I'm here, I will be invaded. And otherwise, I don't see anything happening. So that means that nothing happens. So there's none. None. And so I stay in the open state. Whoops. And I'm still age 0. And now I do the aging process. I just always do this at the end of the time step. I age everything. So it goes to an age of 1. So my end state now is still open, but my age is now 1. Okay. And next, I'm going to roll that troublesome dice. I'm going to roll it again. Get a 3. So I'm sitting here. If I had rolled a 1 or a 2, I would have been invaded. So no, I did not get invaded. So I rolled a 3 and I did not get invaded. So there's no transition again. Sorry. And I stay, so that means I stay in open, but I was in age 1 still. And now I'm going to do the aging, yes. And aging, I've reached the limit of the age range for open. So I'm going to incur this deterministic succession transition. I'm going to move into the closed state. And the start of the closed state is age 2. So my age hasn't been reset. So I now have an age of 2. I'm going to roll my dice again. For the time step 3, I got a 5. This is going to be a boring simulation. So no transition again. Come on, dice. So I'm going to stay in a closed after the transition. I'm still age 2. I'm now going to age. That's going to make me closed age 3. And let's hope for a fire here just to get something interesting happening. 1, yay. So we get a 1 here for this next transition. So I roll a 1 or 2 or 3. That means I incurred a fire in this transition. I mean, in this time step. So that sends me back, and we put it in age 0. We define that we reset the age. So here I had a fire, and I ended up back at open time step age 0. Now I'm going to age, yes, and I move it up to age 1 right away. And this is a little subtlety, but that's what the model algorithm will do if I don't tell it otherwise. So now we're here, we're age 1, and I'm gonna roll that dice one last time to see what happens on the 5th time step. And we end up with a 2, which we rolled a 1 or a 2. It was a probability of 0.33 that we get invaded, so we will actually get invaded. We got one of the more interesting trajectories for this little playing piece. So we rolled the 2. We were invasion, right? We ended up in exotic. The age didn't get reset, so we would have been still 1. We would have done the aging afterwards. We would have ended up at the end exotic times age 2. So that says that this cell here, if I ran it forward in STSIM, if I had started it in age in class 0 open, and I started at age 0, it would have ended in exotic 2. So if we look here, we can then say, you know, this ended up as exotic 2. And we can repeat that then. The computer now will repeat that same process for every one of these other cells on the landscape, right? And if we do that, we end up with something like this. So let's just go back to the full screen. Whoops. No, I went to the wrong place. Let's try that again. I'm gonna go like the right screen. Display settings, swap. There we go. So I went and I repeated this 16 times. When I did it, I didn't end up in E2 like we did. I ended up in open age 1. I actually did the 16 times. I didn't do it with dice. I'll have you know, I did it in the software. And so this is what I would have ended up for one time through rolling the dice across all 16 cells, right? And now that's just what we call one Monte Carlo realization. This is one possible future of our landscape. If we then repeat this, say 100 times, each time we'll get a different value for each cell, and we can summarize, you know, this over all the cells across all the Monte Carlo realizations. Actually, this is just the summary of this here, of one Monte Carlo, sorry. This is how the proportion of open cells in here, proportion of closed and exotic. So already we can see, you know, get projections for one Monte Carlo, but again, if I do this 100 times, each time I get something different, and we can look at the variability across our Monte Carlos in how much open, closed, and exotic we project there to be 5 years out. Okay, so that's the essence of the STSIM algorithm. It really isn't any more complicated than that. You know, you could, as you can see, is either develop this in a spreadsheet, in R, you get a basic state and transition simulation model going very quickly. What you'll see over the rest of the next 2 days is that, you know, there's a lot of sort of subtleties to this stuff in how you set up these models to be a little bit more complex than what we've shown here. And it's just most of the tools and the levers available in STSIM are just simply there to make it easier for you to do complex dynamics, and we'll get into that over the rest of the course. So that's the end of